For this recording, we're going to solve polynomial equations that have complex solutions. So very cool stuff. We're going to be able to use algebraic and graphic strategies. So maybe we'll look at the table to see if we can find any zeros, and then using our knowledge of the remainder theorem, we'll try to reduce this into a quadratic. And then we can always solve a quadratic, right? We have the quadratic formula. And so let's look for this fundamental theorem of algebra. It sounds complicated, right? But it also sounds important because it says the fundamental theorem of algebra. Well, it turns out it's this. It's basically saying if you have a polynomial of degree n, so let's call n, let's use a concrete number, like 2, right? Let's start simple. That means the function has at least one zero in the complex numbers. Okay, that just means there's one place where the function is going to cross the x-axis, or there is one complex number that will solve the equation. Now, we know that complex number solutions, imaginary numbers, always come in pairs, right? So for a function line is always going to cross the x-axis. If we just have a line, it's always going to cross the axis somewhere. And if it's a parabola, it might not cross the x-axis. It might be up here, but then in that case, we'd have two imaginary solutions, right? So they would come in pairs. Now, what this corollary is saying is really important. It's saying if we have degree n, so let's stick with 2 as our degree. So we're talking about a quadratic like this. Then the equation has exactly n solutions in the set of complex numbers. So that means if you have a quadratic, there are exactly 2 solutions, okay? Provided that each solution is repeated, twice is counted as 2. So if you have something like this where it comes down and sits right on the x-axis, and that's considered to be like x equals -3, for example, we will call that 2 roots, -3 and -3. So they'd be the 2 equal solutions. Okay? Certainly, imaginary solutions, you're going to have 2 of them there, and a lot of times you just have 2 x-intercepts, right? You have 2 places where the function crosses. All right, so when we have a polynomial of degree 3 here, we're expecting there to be 3 complex roots. They might be imaginary. If they are imaginary, they will have to be an even number of them because they always come in pairs. So with 3 roots, we know that at least one of them must be real. And so we're going to look at our table. And so let's put this function into our calculator and look at the table. All right, so enter that function, please, and do y equals. If you don't have a calculator, you can just pretend you do. So at this point, we're going to look in our table. So we're going to go to second table, and we're going to scour that table for any zeros. And wait a second, I see one right here. When x is 3, y is 0. So right away, I have a root. Let's head back to our workspace here. Now, I have to divide that in to this function. I have to divide the whole thing by the factor x minus 3. Or I can use some synthetic long division and divide 3. So I'm going to go 1, -3, 1, -3. Those are my coefficients of the polynomial. And I'm just going to do up the math. So bring down your 1, 3 times 1. -3 times 3, 0, or plus, so 0. 3 times 0, 0. Adding. 3 times 1, 3, adding. So now I interpret that. The 0 is the remainder. That's good news because I thought 3 divided evenly, or x minus 3, the factor, divided evenly into the polynomial. I thought that 3 was a 0 or a root, which it is. So what that leaves me with is x squared, that's a square. That's the linear term, the x, so it's like 0x, and there's a 1. So I have x squared plus 1. All right, so now I need to solve this. Okay, it's equal to 0, so I still have an x minus 3 over here. I know this is going to give me a 0, and now I have to solve this part. Okay, I'll work that out over here. So I'm going to get x squared by itself. I'm going to square root both sides. The absolute value of x equals I, the imaginary unit. So that means x is equal to plus or minus I. Alright, so my roots, the solution set, I was expecting 3 roots. I do have them, 3, I, and -I. These are complex conjugates, as expected. If there's 1, there's going to be 2, and they're going to be conjugates. All right, in this next example, we have some work we can do algebraically. I see a common factor throughout here of 3x. So let's go ahead and take that out. Let's get as far as we can algebraically first. So we take out a 3x, we're end up with x to the 4th plus 8x squared plus 16. And that's all equal to 0. So obviously this is going to lead us to a root of 0. Anything times 0 will give us a 0. But I bet we can break this down. This is not a quadratic. And when we look in the table, if you want, go ahead and peek in the table, you don't see any other real roots that appear. However, this is a particular polynomial that we can factor using quadratic techniques. We studied that earlier. So let's take our 3x over to the side, and let's take this and see if we can factor it by treating it basically like a quadratic. Because there's 3 terms. I'm going to put x to the 4th, 16. I'm going to find out what adds up to be 8x squared that multiplies to be 16. So that would be a 4x squared and a 4x squared. So I've basically split that 8x squared. This is like a perfect square trinomial. So I've got x squared as a GCF on each side, and I've got a 4. So it looks like when I factor this, I have x squared plus 4 squared. Okay, so now to proceed, obviously 3x equals 0. We've got a 0 right there, as we expected. And for the x squared minus or plus 4, that again is going to lead to imaginary roots. I could use my quadratic formula, and I could have used the quadratic formula earlier in this, but I just recognized I could solve it easily with square root. So either way. So we'll work this one out. X squared equals negative 4. And when you square root both sides, you're going to get your imaginary roots. So x is equal to plus or minus 2i. Now, of course, that'll also happen here. I could work that out again, and again I would get plus or minus 2i, so I'd get those 2 roots. I'll just kind of do a shortcut and copy that. So if I grabbed all that right there, pasted it over here, that's what would happen if I set this equal to 0. So I have 1, 2, 3, 4, 5. I've got 5 roots. 2 of them are repeated. Okay, so that's what our corollary of the fundamental theorem of algebra said. There would be exactly 5 roots as long as we consider these to be distinct roots. So again, when I list out the roots, I will not list those repeats. Okay, so it's 2i and negative 2i. Thanks for watching.